Okay, so we're on chapter 12, section 1. And we're talking about the fundamental counting principle and permutations. Pardon? Did I what? I had to take my daughter to daycare, and then I was late. If you want to know the whole story, we were on the way out the door, and she had a blowout. So then I was late. So then, because I was going to take my pickup home and then walk, but I was already late, so I just parked out there. Yeah. Don't worry about it. You don't need to know where I live.
Oh, okay.
I just live a block away. I would not want to walk. Yeah. So no, I'm feeling good. I was just a little behind after she blew out. Yeah. Yep, still got the same one. Still drives. Just not very often. Alright, so 12.1, first thing, let's talk about the fundamental counting principle. So what we're doing is basically we're going through and discovering how many ways can something be done. Okay, so like, I don't know, an easy example, you go to Subway. Hey, you got your different types of bread, you got your different types of cheeses, you got your different types of meats, your sides or your toppings, your sauces, stuff like that. Okay, we want to know maybe how many combinations of sandwiches could you have. Okay, if you went every day, how many days would it take you to eat every single type of sandwich with every combination on it? Does that make sense? It's going to take a long time. Okay, but that'd be just an easy example to look at. Okay, so taking a look here on the fundamental counting principle, they go through and they are doing sandwiches. Okay, and I'm not going to copy this all down because this is going to take a lot of time to not get a ton accomplished. But you take a look there. They tell you, suppose you own a small deli. You offer 4 types of meat: ham, turkey, roast beef, and pastrami. Okay, so you got 4 types of meat. Okay, and then you have, where am I at? 3 types of bread. You got white, wheat, and rye. Okay, so you got 3 types of bread. Okay, and then you go on. I'm missing something, aren't I? Oh, no, we're good. Okay, they want to know how many choices do your customers have for just a straight meat sandwich. No cheese, no sauce, nothing like that. Okay, well, you can see there, first you have to choose what kind of meat you want, right? Okay, so there's 4 options there. And then after that, if you chose ham, if you're looking in your book, you chose ham, well, then you got 3 choices for bread, right? Okay, so how many total combinations can you get if you have ham? 3. You could have ham on white, ham on wheat, ham on rye. Right? Okay, or if you chose turkey, you would have 3 more. Same thing, right? Turkey on wheat, turkey on white, turkey on rye. And roast beef, same 3. And then pastrami, same 3. Okay, so you can count down the right side there, and how many total choices do I have? Okay, you have 12 total choices. What do you notice? What's that, Kobe? You multiplied, right? Isn't 4 times 3, 12? Okay, and that's all the fundamental counting principle really is. Okay, you figure out how many options do you have for this event, event 1, how many options do you have for event 2, and so on. Maybe you have 5 events, it's how many options you have each time, and then you multiply them together. Okay, so let's go ahead and say, Brody seems like maybe he's a little high maintenance, so he's got lots of clothes to pick out in the morning. Okay, so let's say Brody has 5 different shirts he's going to choose from. He's got 4 different pairs of jeans. He's got 20 different socks. Brody likes socks. Fuzzy socks, Christmas socks, Winnie the Pooh socks. Okay, And then he's got 4 different types of boots.
There's so many.
Because Brody wears boots. Okay? I want to know how many different outfits might Brody show up at school in. Okay? You take 5 times 4, which is?
20.
Times 20, which is? Times 4, which is?
Jeez.
Okay, that's kind of crazy, right? It's not like we had that many choices. Okay, but that extra 20 socks in there puts a big twist in things. Okay, so you just got to realize this doesn't, this is maybe he wears a blue shirt with his black jeans, or maybe he wears his blue shirt with his yellow jeans. Brody's got those yellow skinny jeans. Okay, maybe he wears his blue shirt with his blue jeans, blue shirt with his green jeans. Okay, well then, after he does that, then he's got to pick out of his 20 socks, and then he's got to pick out of his, so when you really think about it, you can kind of see how there's so many choices. Okay, but just at first glance, it's kind of hard to believe that there's that many different outfits. Okay, and that's just your fundamental counting principle. Okay, you're taking however many combinations of each one you have, however many choices you have in each one, and you're multiplying them all together. And if you wanted to, you could make a chart just like they did on page 701 for all of that also. Okay, and then you could just count down the right side. Now that's kind of a waste of time though, right? If you know you can just multiply them together, you're kind of wasting time if you're going to do that. Okay, so now when we're really using it, okay, we're looking at example 1 here. It talks about criminology. Okay, it says police use photographs of various facial features to help witnesses identify suspects. Okay, one basic identification kit contains 195 hairlines. You can already tell this is probably going to be pretty big, right? Okay. 99 eyes and eyebrows. 89 noses. 105 mouths. And 74 chins and cheeks. A lot of different options, right? Okay, but when you think about it, people have tons of different hairlines, tons of different eye and eyebrow shapes, tons of different noses, mouths, cheeks and chins. Okay, so to figure out how many total options there are, okay, the developer tells people that there's billions of choices. Okay, and you can multiply these all together on your calculator. Okay, and you would get what? Huh? What's the last number? 986. Oh, I thought you said 586. Okay, so there's that many different, basically, drawings that they could come up with for suspects, right? Okay, and then the next part says a witness can clearly remember the hairline and eyes and eyebrows. Okay, so now you just multiply these 3 and you get what? A lot more reasonable, but still probably pretty hard to identify, right? Okay, so once you eliminate just the hairlines and eyes and eyebrows, you're down to 691,530. Still a lot of people to sort through, right? Or a lot of pictures, I guess. Okay, so they would probably have to go through, and they'd probably have to be like, okay, it's definitely not that nose. Maybe they can cut the noses down to 10 or something like that and slowly reduce. Okay. Just a small example there. Now, another good example is like with license plates. Okay. Okay, so here in Sydney, first 2 numbers are always 39. Okay, so across the state, anybody know how many counties there are? 90 what? I think there's 93. 92 or 93, I can't remember. I think there's 93. So, how many, I mean, let's forget about the Lincoln and Omaha. Let's say we start at 1. Okay? So for our county, we have a total of 93 choices, right? Okay. Now, for those 93, how many choices, because our county is always 2 digits, right? So it's 2 digits, dash, and then what? 4 numbers or letters, right? Sometimes letters. How many choices are there for this first number? 9. 0 through 9, right? That's actually how many? 10. Because 0, it could be 0 if it's a single digit, right? Now they wouldn't probably write it, okay, but it would have to be like a space. Okay? How many choices for this one? Now, it's only a 0. Well, no, you're right. It would be 10, because if it was in the 80s, I was thinking because of the 3, but if it was in the 80s, it could be 89. Okay, so there's 10, 0 through 9, right? Now, what about this one? Now, could this be a number?
It could be a letter.
It could be a letter, and it could be a number. So there's how many letters in the alphabet, and there's how many numbers. So a total of, same for that, right?
Yep.
Same for that. Now, obviously, this isn't counting like a special license plate, right? Where this dash isn't there. So how many total options are there for license plates in the state of Nebraska? How many? 14,400. Would that reduce significantly if I just asked, what about in Cheyenne County? Yeah, because then I would know that this number out in front's 39. Hey, then what would it be? What is it? Huh? 36 times 36 times 36 times 36 is 144. Is our last number not right either?
I hit the wrong button. The last number wasn't right.
Seemed pretty small.
Okay, it's 1,000,006.
1,600,000.
No, 1,067. My bad. Or 100,000,060. Yeah, you have to do the CAD. 167.
167, comma,
961.
961,
Comma 600.
comma 600. That's better. That's the license you added?
You can't multiply 36 by 4.
No. Right. Gotcha. Okay, so this is how many options there are in the state of Nebraska. Okay, and then I take off 10 times 10 is 100, right? So if I do just the county, get rid of 2 zeros, so I have 1,679,616 in the county. Still way more people than, or way more license plates than what vehicles we probably have in the county, right? Well, maybe not vehicles, but people for sure. Okay. Again, that doesn't include your special license plates, stuff like that. Okay. Just a good example of how many options there are. Now, what about this one? I don't want you to tell me, but does anybody know their social security number?
Yes.
Okay, how many digits is it?
A lot.
There's 1, 2, 3, right? Correct? Okay, and each person in the U.S. has their own social security number, correct? Okay. How many choices for the first number? We can do this in our head. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. What is that? 1 trillion. So, I don't know for sure how they do it, but at some point something's going to have to be reused, right? So it's kind of weird to think about. You might have the same Social Security number as somebody who died, right? Unless they change it. I don't know how it works. Okay, but I mean, logically thinking, that's 1 trillion. I forget, isn't there like 300 million in the U.S., right? Okay, so people die and people are born. So I don't know if they reuse it. I don't know how they do it. As far as I know, anybody I've ever talked to only has 9 digits in their Social Security number. So I don't know what they do. I don't know how they do it. I don't know if you end up after so long reusing a Social Security number. I have no idea how they do that. Okay, but just something to think about. Yeah, well, they started to. I'm like, no. I don't want to know your Social Security number. That's not something you just tell people. It's probably the most private thing you need to keep to yourself. Maybe even more so than your credit card.
I have no money, so go for it.
Yeah, exactly. Credit cards can be canceled. Your Social Security number can't be canceled. All right. Now, the next thing, that was all using fundamental counting principle. Okay? So if you know how many choices you have for each thing, to find the total options, you multiply, correct? Now here, the next thing we're going to talk about is permutations. Okay? It's an ordering of n objects. Make sure I say this correctly. Excuse me. Yeah, the ordering of n distinct objects. No, the number of permutations of R objects taken from a group of n distinct objects. Okay, now, a permutation, the big thing you need to know before we get into specifics is you need to know that with a permutation, the order does matter. Okay, the order does matter. Okay, so what that means is that ABC is different than ACB, which is different than BAC, which is different than BCA. Okay, I'm using all the same letters, and I could keep going with this. Okay, I'm using all the same letters, but they're different. Okay, every choice is different. Okay, it's like if Carissa, Logan, and Jedediah were racing each other on bicycles. Okay, we want to know how many different ways could they finish. Okay, well, if Carissa finishes first, Logan finishes second, Jedediah finishes third. Okay, that's different than if Logan finished first, Carissa was second, and Jedediah was third, right? Okay, Jedediah, you're last both times. Okay, but you guys get what I'm saying. Like, that's different. Okay, maybe the winner gets a reward or something. No, you're bringing donuts tomorrow.
No.
Yes.
Okay, so that's what I'm talking about here. Okay, it's different. The order does matter. Okay, if the order changes, it's a completely different option. Okay, so let's use our ABC. Okay, so now I've done A first, and I've done both options here, and I've done B first, and I've done both options here. Okay, now let's do C first, and then I have AB, and I have CBA. Are there any other options that I can come up with? No, because I took A, and I did my 2, I did B, and I did my... So there's total of how many options? 6. Okay, now this is something new to you guys that you've probably never used. Does anybody know what this means?
3.
No, it does not mean 3. That's 3 factorial in math. Okay? And what that means is that I'm taking 3 times 2 times 1. So I'm reducing one number every single time. Okay, so if I had 27 factorial, okay, let's do 26. 26 letters in the alphabet, right? How many different ways can I arrange them? Well, you do 26 times 25 times 24 times 23 times 22. Because once you've chosen, let's say I chose Z, okay, well, the second option, how many choices are there? And then let's say I chose B, and then now how many choices are there? 24. And then I chose C, and now there's 23, and so on. Do you guys get where I'm coming with this? So it's the same idea as what we did up here with the fundamental counting principle, except once I've chosen one, I can't use it anymore. So the next time I have one less. You guys get where I'm going with that? Okay. So, yes, there is. Anybody have a TI with them?
I do. Is this a TI?
That'd be a TI. It is. Oh, maybe there isn't one on these ones. Yeah, any of your graphing ones are going to have it.
Oh, of course.
I don't know that these have it. I'll have to look. Where at? Yes.
There we go. A, B, C, C. That's on it. Just
No,
trying to
that's a
make
fraction.
myself feel better.
Okay, I'll have to look it up after we finish here. Okay, and see if there's a factorial. Hey, all your graphing calculators have it. I know the Casios have it. Okay, but we'll go over it in a second. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 15 of us in the classroom right now. Okay? When Carissa brings donuts tomorrow, we want to know how many different ways can we all go get our donuts. Okay? Well, at first, how many people could go first? 15. And then how many people can go? And then 7, 6, 5, 4, 3, 2, and then 1, right? Okay? That would also be signified as 15 factorial. Okay? What number does that come out to? How many different ways could we go get donuts tomorrow, Lorelai, when Carissa brings donuts?
Do you really have to use the 1? It's 1.3 times 10 to the
1.3 times 10 to the 12th. So that's in scientific notation. Do you guys remember how to get rid of that? How many zeros? 12. So I have 1, 3, and then I need... Why? Because I already moved my decimal one spot. So I'm taking this decimal, I'm moving it 12 spaces. So I'm going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you fill in your zeros. That's a big number. That's kind of crazy to think about with just us in the classroom, huh? So I have 1, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have hundreds, thousands, million, billion. So we have 1.3 trillion different ways that we could each go get our donuts. We'll try one way tomorrow. Chris, I'm just giving you a hard time. You don't have to bring donuts if you don't want to. Okay? Okay, so that would be a permutation. Now, another thing with permutations, okay, that's when you're using all of it. Okay, so that's when we're using all of our students. Now, we're going to come across something. I only have one wrestler in here, just Derek. Okay, we're going to pretend Jack, Cade, and Kobe all wrestle also. Okay? And you're all overweight. So none of you can have donuts. Okay? So, the next thing we're going to talk about is there's 15 of us, Okay, so there's 15 total, but only 11 are coming up to get donuts. Okay, and that takes us to that green box down at the bottom of page 703, where it talks about permutations of n objects taken R at a time. Okay. And the way we're going to set this up, that's an N. Carissa, that's an N. Just giving you a hard time. Okay. This is going to be set up in your calculators. This is going to be an option. Okay. It is.
Oh, I see it now.
It's here. I just got to remember where it's at.
I don't see it on mine.
Did you find it, Jack?
Oh, it's there. I have mine.
It's right there,
Yours
right?
is a different
It's the PRB.
Yep, there it is.
That's what I thought.
So you go to the PRB. Oh, there's your factorial too.
What?
Okay.
Where?
PRB, which stands for probability.
No problem, right?
Okay, you guys find it? Yeah. Okay, so then there's your NPR, and then there's an NCR, which we'll work with later. Okay, so NPR is your permutations. What's that? Yep, that's yours. Okay, so everybody found permutations, and now we have our factorial also. Okay, now, this can be done by hand, but why would you do that? Right? Why would you do that? So if you want to go ahead and copy it down, this is equal to n factorial divided by n minus r factorial. Okay? But there's no reason to do that if you have your calculator. Okay, so what we need to be aware of is n is your total number. R is how many you are picking. Okay. I like to think of this as, and I'll say this, I'll say N pick R. Okay? So you have, if we're talking about how many people are getting donuts, okay, but those 4 are wrestling, it's going to be 15 pick 11. Okay, so in our calculators, you can put 15 pick 11. I believe in your TIs you have to do this, and then do your NPR, and then do your 11. Okay, and what do I get? Times 10 to the what? So I have 5.4, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, times 10 to the 10th. Okay, so you have 5, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0. So now I only have 54 billion, right? So dropping 4 of them out takes me from 1.3 trillion to 54 billion. Okay, so it makes a pretty big difference in a hurry, right? Okay. All right, let's flip over. There's another good example of this here. Okay, example 4. 20. We get out of here at 20? Okay. We're probably going to just finish this lesson out, not do a lot for homework, and then work on it tomorrow in class. Okay, is kind of my plan. Example 4 says you are considering 10 different colleges. Before you decide to apply to the college, you want to visit some or all of them. In how many orders can you visit 6 of the colleges first? Okay, so you have 10 colleges, but how many do you get to pick? You only get to pick 6 of them. So how many different ways can you visit these colleges? Okay, so maybe you go to Nebraska, then Chadron, then Colorado State, and so on. How many different orders? Somebody ask me and read it to me.
151,000.
Okay, so out of 10 colleges, if you only pick 6 of them, you can visit them in 151,200 different orders. Does order matter with permutations? Yes, order matters. Okay, so is going to Lincoln and then Colorado State the same as going to Colorado State and then Lincoln? No, those are 2 different ways. Okay, so just be aware of that. That's why these numbers are so big. It's because all you have to do is take one school and move it, and it changes everything completely. Okay. Now, what if I wanted to visit all 10 colleges? Then this would be 10, pick 10.
Yikes.
Okay. Now, if I chose all of them, what is this the same thing as doing? The 10. The 10, yes. No, the 10 factorial, right? Isn't that the same thing? Because up here when we were using that, we were using all of it, right? Okay. So if you ever do a 10 pick 10, whatever it is, and you use everything, you could just do 10 factorial. So, do you actually have to use 10 factorial if you don't want to? Or could you always use your permutations button? You could always use your permutations button. Okay, remember, you're asking yourself, how many total, and then how many are you picking? Okay. Not too bad, right? Okay. Now, there's one other catch.
Of course.
Always is, right? Okay. Permutations with repetition. Okay. Permutations with repetition. Your box there tells us the number of distinguishable permutations of the number of distinguishable permutations of n objects where one object is repeated q sub 1 times, another is repeated q sub 2 times, and so on is blank. Okay? So, all that means is there could be multiple things being repeated, right? And I don't know how many times it's being repeated, and that doesn't necessarily matter right now. Okay, but this is going to be n factorial divided by, so are you using all of your things here?
Yes.
Yeah, you are right now. Divided by q sub 1 factorial times q sub 2 factorial, and so on. Okay, so anything that's repeated, you need to put on the bottom to divide. Okay, so let's take a look down here at this example 5. Their example is the word Ohio. Okay, they want to know how many different ways can I order these letters for the word Ohio. Hey, immediately you notice that the O is repeated, correct? Okay, and there's how many letters total? Okay, so forgetting about the repetition, there would be 4 factorial options, correct? You guys agree with that? This would be 4, and then the second choice you'd have 3, and the second choice you'd have 2 letters, and then the last choice you'd only have 1 letter left. Okay, so your total is 4 factorial, but you got to divide that by how many times something is repeated. Okay, so there's 1 letter that's repeated twice, right? So I need to divide by 2 factorial. Okay, so you can just plug that. If you do that, use your parentheses. Okay, use your parentheses, otherwise it'll do 4 times 4 factorial divided by 2, and then it'll do factorial of that. Okay, so 4 factorial is 24 divided by, which is 12. Okay, did I get that right? 4 factorial is 24, right? Okay, so there's actually 12 different options, because does it matter where I put those O's? No, because they're going to be the same in both places. You're not going to tell which one's which. Okay, let's do the longer one that they have there. They have the word Mississippi. Okay, so we have the word Mississippi. How many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what goes on top, Lorelai?
11.
What's that called? What's it called? Starts with an F. Factorial. I have 11 factorial on top, because that's how many ways I could order them. But again, it doesn't matter if I put this S first, or that S, or that one, or that one. They're all the same, right? They're all S's. So when I divide this, the S's yield me 4 factorial. What else repeats? The I's, how many I's are there? 4 factorial. Okay, notice I'm multiplying. And then 2 P's, right? So then I need to divide by 2 factorial. Anybody have 11 factorial for us? Can you get it for me, please? Did you get it right?
It is, I think so.
Okay.
399, 160.
Okay. And I divide 39,916,800 by 24 times 24 times 2. And my final answer is, okay, so obviously looking at this number and looking at this number, when things repeat like that, it makes a pretty big difference, right? Okay, so just be aware of that. Okay, things repeating or things with repetition are very different from things without repetition. Okay, so we talked fundamental counting principle, okay, permutations, and permutations with repetition. Okay, now it wasn't bad here, I don't think. When you have to start picking them out on your own, that's when it's going to get challenging. Okay, what I want you guys to do, I do want you to do a few things for me. On page 705, just go ahead and start this on your assignment for me. We'll pick this back up tomorrow. But I want you to start on page 705. Just do 5 through 14 for me. Give those a try. So you have a few problems that you need to do, so you can do a few on your own here. Yeah.